Lesson 8.2, Relative Rates of Growth. What we'll learn is how to compare rates of growth using L'Hopital's rule. Here's the definition of faster, slower, and same rate growth. When we're comparing two functions that are both growing sufficiently large, when we get the result of infinity, that tells us that the numerator is dominating, and so we can say that f of f grows faster than g. Now, if the fractions were reversed, the numerator denominator reversed, and we found that the limit was 0, then this tells us that the denominator was dominating, and we know that f again is faster than g. If we compare two functions and we find that we get a limit, then the definition says that they're growing at the same rate. Let's take a look at comparing e to the x and x squared. So this is an indeterminate form. We're going to use L'Hopital's rule, and we're going to get e to the x and 2x, which is, again, an indeterminate form. And this should have been the number 2. And when we compare that, that's going to be infinity. Being infinity means that this was dominating. So we can say that e to the x grows faster than x squared. Let's take a look at comparing the natural log of x with these two. So natural log of x and x. This is a infinity over infinity situation. I'm going to use L'Hopital's rule. As x approaches infinity, we get 0. Getting 0 means that the denominator was dominating, which tells us the natural log grows slower. We can do the same kind of thing again. This is going to be infinity over infinity. And we are going to take this and we're going to write a product. Instead of we could take L'Hopital's rule twice, but if we separate this, we've already taken this limit. We just did it above right here, and we know that this goes to 0. And as x goes to infinity, then we know this goes to 0. And so without using L'Hopital's rule, just using prior results, we can get 0. All right, let's go ahead and compare these two rates of change. So the limit as x approaches infinity of x plus sine of x over x. So this is an indeterminate form, infinity over infinity. Now we're going to use the strategy of separating the fractions like this. All right, and when we do that, we can see that as x approaches infinity, this is going to dominate. Sine of x is just going to go back and forth from -1 to 1, but this is going to dominate. So this answer is going to be 1 plus 0, or the answer is 1. All right, when we get 1, then that tells us that both of these are growing at the same rate. So even though we're adding a little sine of x as x gets infinity, really it's these two that are really creating the comparison. Sine of x isn't doing much. All right, we want to compare two logarithms and show that let a and b be numbers greater than 1, and we want to show that they grow at the same rate. So I'm going to go ahead and start here, limit as x approaches infinity of log base a of x over log base b of x. And we want to see that they grow at the same rate. Now let's remember one of our identities here, that log base a is the same thing as natural log of x over natural log of a. So I'm going to write this in terms of the natural log. I could have done it with log base 10 as well. Natural log of x over natural log of a. And then this will, same thing, natural log of x over natural log of a. And we can see we can do some reducing. This should have been AB right here. And this can have some reducing. And then we get equal to the limit as x approaches infinity on the natural log of b all over the natural log of a. Now these are both constants, so that this is the answer, natural log of b over the natural log of a, which is a constant, and that tells us that both of these grow at the same rate. So no matter whether the bases are different, these logs grow at the same rate. Okay, transitivity of growing rates. If f grows at the same rate as g and g grows at the same rate as h, then f grows at the same rate of h. So let's take a look at these and show that they're growing at the same rate. And what we want to do is, they're pretty complex looking. What we'd rather do is compare them with something simple that's easy for us. And what I'd like to compare them with is, I'm going to compare them with h of x, which is x. Now, why did I pick x? Well, the very simplest form here, the square root of x squared, if we disregard the 5, as we go to infinity, the 5 is not going to make much of a difference. This is really close to x. And when you take square root of x and you square it, you're getting close to x as well. So that's why I picked this h. All right, so let's go ahead and take a look at the limit as x approaches infinity of f of x over h of x, and that's going to be the limit as x approaches infinity of root x squared plus 5 all over x. This is an infinity over infinity situation, so I can go ahead and use L'Hopital's rule. So that'll be 1 in the denominator, and then this will be 1 over 2 root x squared plus 5, and then using the chain rule, 2x. The 2's will reduce, and we can see that we can use L'Hopital's rule again. Or actually, I think what I would rather do is I'd like to get this into 1 square root, which is probably what I should have done in the beginning. So this is going to be x squared all over x squared plus 5. And we can see by the dominance rule here that we're just going to look at the coefficients here. And this whole thing is going to actually get close to 1, and the square root of 1 is 1. And I think I could have done that way back here without using L'Hopital's rule. So I think I've learned my lesson, and maybe what I'll do is I'll do that when I compare g of x with h of x. Limit as x approaches infinity, and we're going to get 2 root x minus 1 squared all over x. So this is going to be the same thing as limit as x approaches infinity, and this is going to be now getting this x within this square root here, that's going to require that I do 2 root x minus 1 squared all over root x squared, like this. And then I'm going to take a look at the limit as x approaches infinity, and then this I can write this way, 2 root x minus 1 all over root x. And again, we can see the domination right here is going to be the same, so this is going to be a 2 within the argument, and then 2 squared is going to be 4. So we're getting a constant here. It's not the same constant as this one, but these grow at the same rate. And since we know that these two are growing at the same rate and these two are growing at the same rate, and they have this connection of h of x, which I said was x, then f of x grows at the same rate as g of x. And this is the end of the screencast.